Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about molecular geometry and bonding domains. So we're going to talk about how atoms arrange around each other and give an overall three-dimensional shape depending on whether it has bonding domains or lone pairs. So let's get into this video. So the first thing that we're going to talk about is the difference between a Lewis diagram and the actual particle in 3 dimensions. So the Lewis diagram gives us some really good starting information. We could see what atoms are connected to which and where there are going to be lone pairs existing. But Lewis diagrams are written on a flat board or a piece of paper, and that's a 2-dimensional surface. But all of these molecules and particles are 3-dimensional shapes or objects. So we're going to need to start taking the ideas from our Lewis diagram and thinking about these particles in 3 dimensions. So what dictates this is this acronym called Vesper. So VSEPR stands for valence shell electron pair repulsion theory. And all this is telling you is that electrons are going to repel each other as far away as possible, and this is what's going to dictate the 3-dimensional shape of all the particles that we have. So let's take a look at this Lewis diagram using some generic A and B terms. So we've got some areas around the central atom A. We've got some bonding domains, or things that are connected to A with a bond, and we have non-bonding domains, and we represent these as lone pairs. So these electrons, whether they're in bonding pairs or lone pairs, are going to want to repel each other as far away as possible around the central atom, and that's going to dictate the 3-dimensional shape, is our bonding domains and our non-bonding domains. So let's start to talk about the major electron domain geometries that exist. And it's going to be dictated on the total number of bonding domains and non-bonding domains on the central atom. So if we have a central atom with 2 domains on it, this is going to be the linear category, and it's going to have a bond angle of 180 degrees. If we have 3 domains around the central atom, this is going to be trigonal planar with a bond angle of 120 degrees. If we have 4 domains on the central atom, we call this tetrahedral. And you've got to remember this is in 3 dimensions, and since this is a 3-dimensional space, the furthest away that these domains can get from each other are 109.5 degrees. Not 90 degrees. And then if we have 5 domains around the central atom, this is called trigonal bipyramidal, and there are 2 different bonding areas. We have 120 degrees around the equatorial positions, and then we have 90 degrees between an equatorial position and an axial position. And then the last category we have is 6 domains total. We call this octahedral. It's going to form an octahedron with 8 faces, and they all have 90-degree bond angle. So what we're trying to do here is get from a chemical formula to a Lewis diagram to a 3-dimensional diagram and eventually a space-filling model of how this thing exists in 3 dimensions. So now that I've just told you the molecular geometry domain, or the overall molecular geometry, let's get into the subcategories of shapes that could be under each molecular geometry. The general rule for this of all of them besides octahedral is you could take the number of domains and subtract 1, and that will tell you how many shapes that you have under each variation. So for the linear category, we had 2 domains, and if we subtract 1 from that, we only have 1 possible shape for linear, and that's linear. So here I have a ball and stick model or molecular modeling kit, and I have modeled carbon dioxide, and you can see that it has 2 domains and it's got a 180-degree bond angle. It is linear in shape. So the next major category that we have is trigonal planar, which has 3 domains. And if we subtract 1 from this, we have 2 possible shapes. If we have 3 domains and all of them are bonding domains, we have trigonal planar, trigonal planar. And here we've got something like sulfur trioxide. It's got 3 domains around the central sulfur atom, and we could see that it is planar, it's flat, and we've got a bond angle of 120 degrees. The next shape under trigonal planar is if we have 2 bonding domains, 1 non-bonding domain. So one of these domains is a lone pair, and we usually visualize this with just empty space. There are electrons occupying this empty space, but generally we draw the domains as sticks. So you can see that this is a bent shape with bond angle 120 degrees. The next thing I want to mention here, though, is if you have lone pairs have higher repulsion values. So what's actually going to happen is this bond is going to get squeezed together, so it should actually be slightly less than 120 degrees when you've got lone pairs on the central atom. So the next category that we have is tetrahedral, or 4 domains. And if we take our 4 domains and we subtract 1 from it, we should have 3 possible shapes under this category. The first shape is if we have 4 domains, all of them are bonding domains, and no non-bonding domains, we'd get this tetrahedral shape. So something like methane has 4 bonding domains, no non-bonding domains. So this would be tetrahedral with a bond angle of 109.5 degrees. The next category we'd have is 3 bonding domains, 1 non-bonding domain, which would give us trigonal pyramidal. So we could see that it's this trigonal shape, it's like a triangle, but if we sit it down flat, it forms a little pyramid shape. And that's due to the lone pair at the top. So something like ammonia, NH3, has a lone pair on top, and our bond angle is going to get squeezed down by that lone pair a little bit. So it's going to be a little less than 109.5 for the degrees angle on ammonia. The last category under tetrahedral is going to be 2 bonding domains, 2 non-bonding domains, such as water. And water is going to be tetrahedral bent. And the bond angle is going to be even less than that of ammonia. It's going to be even less than 109.5 compared to ammonia's. And that's due to 2 lone pairs squeezing this bond together. So the other thing that could affect our bond angle besides having lone pairs on the central atom is if we have a double bond within our molecule. So something like this has a double bond, and it's got 4 electrons within that double bond, and that's going to have a high repulsive value. Therefore, the bond angle between the double bond and the next bond is going to be greater than that of normal. So something like this would be 120 degrees normally, but the double bond is going to push on these single bonds further away. So between the double bond and the next bond, it's going to be greater than 120, and between the 2 single bonded areas, it's going to be less than 120 degrees. The next category is trigonal bipyramidal, or 5 domains. -1 means we have 4 possible shapes. If we have 5 bonding domains, no non-bonding domains, that's trigonal bipyramidal. In order to visualize this, most modeling kits don't have the capacity of having 5 or 6 domains, so you might want to use a digital modeling software, something like the V.I.P.N simulator from University of Colorado. They have a really nice simulator where you could put lone pairs and visualize the bond angles. So I suggest using that for your 5 and 6 domain variation. So for our 5 bonding domains, no non-bonding domains, we have 2 possible areas where we're going to form bond angles. The first position is called the equatorial position, and if you know anything about the Earth, the equator is around the central part of the Earth. So if we're thinking about our trigonal bipyramidal particle, we're going to have 3 domains around the central area of this called the equatorial position, and those equatorial positions are going to form 120 degree bond angles. The other 2 areas we have on the top and bottom are called axial positions, and between an equatorial position and an axial position, you're going to have a 90 degree bond angle. So when you start to put lone pairs on trigonal bipyramidal, you can only put lone pairs on the equatorial position. So you can have either 1, 2, or 3 lone pairs on a trigonal bipyramidal molecule. The next shape we would have under this category is 4 bonding domains, 1 non-bonding domain. And this is going to form a shape called a seesaw. And if any of you have ridden on a seesaw, or some of you may call it a teeter-totter, you've got this pivot system, and then you've got children on either side that bounce up and down, causing the seesaw or teeter-totter to rotate. If you actually go to model this, it looks just like a seesaw, which is where it gets its name from. So the bond angles, since there's a lone pair on the equatorial position, are going to be squeezed in a little bit just as before. The next category is if we've got 3 bonding domains, 2 non-bonding domains, you're going to get a T shape. So it looks exactly like a T. And that's because you have 2 lone pairs on the equatorial position. Therefore, you only have 1 sticking out of the equatorial position, and then you still have got the 2 axial positions. And then the last shape we have in this category is 2 bonding domains, 3 non-bonding domains. All of the equatorial positions have lone pairs, so you're just going to get a straight line, and this should be a linear shape with a 180-degree bond angle. There should be no pushing from either direction since you have equal pushing in all directions. The last electron domain geometry is octahedral, and this is the only time where our number of domains minus 1 falls apart. Octahedral does not follow this pattern, and you only have 3 possible shapes for octahedral. When we were talking about the axial and equatorial positions, the lone pairs for octahedral must go on the axial positions. So all positions at the equatorial location must be occupied by bonding domains for octahedral. So the first shape that we have underneath this geometry domain structure is 6 bonding, no non-bonding, and we would call this octahedral. And if you model this using the V.I.P.N software, we could see that all of the bond angles here are going to be 90-degree bond angles. The next shape that we would have here is 5 bonding domains, 1 non-bonding domain, and we call this square pyramidal, and that's because we form a pyramid with a square base, and then we're going to come up to the vertice at the top of that 1 bonding domain at the axial position with the lone pair underneath of it. And so again, we're going to have 90-degree bond angles, but that lone pair is going to push the square base up a little bit. And then the last shape that we have for octahedral is 4 bonding domains, 2 non-bonding domains, which is square planar. All of these are going to be within the same plane at the equatorial position, and it's going to form a square shape, and it's going to have 90-degree bond angles because the lone pairs are pushing equally from either side. So there it is, you guys. There's the video on molecular geometry and shapes based on Lewis diagrams. So if you enjoyed this video, smash the like button, send it to your favorite lepidopteran, send it to your favorite fennec fox, and we'll see you in the next video.